All right, so tonight we're going to look at convexity, and then we're going to dive into some alternative definitions of interest rates. All right, so convexity, if you remember from last time, is the second derivative of the price yield curve divided by the price. Okay, so let's just take a step back for a second. The price yield curve, as you recall, looks like this. So for any given bond, we have this relationship between prices and yields. And the curve has a negative slope. And also, you notice that it has the property of being convex, which means that the second derivative is positive as R increases. In other words, as we move to the right, you can see that the slope becomes progressively less negative. And so therefore, you can see that two things are going on here. The first derivative is negative, of course, and the second derivative is positive. And therefore, the curve is said to be convex, specifically convex to the origin. And we also saw that this is actually beneficial to the investor because what it does is it creates an asymmetry between gains and losses due to changes in the yield. For example, if we started out here, let me actually draw a new curve here. Let's say, for example, we start out with a yield of 5% and a price of 1,000. If I increase the yield to 6%, the price will drop, of course. Let's say it drops all the way down to 922. But then if I drop the yield by 1%, the price of the bond will go up, let's say, to 1083. And so what we can see here is that when there's a 1% increase in the yield, the price of the bond only drops by $78. But when the yield drops by 1%, the price of the bond goes up by $83. So that's because of the convexity of this curve. If this was a linear relationship, then of course, for the same change in yield, the price change would also be the same. So convexity does work in favor of the investor in this bond. But it does more than that. It gives us a way of helping us understand how sensitive the duration of the bond is to changes in yield. So in other words, if you remember the duration, the modified duration that is nothing but the slope of this price yield curve scaled by the price of the bond. Okay, so if you remember, we formally defined modified duration as here it is. Okay, negative dp dr times 1 over p. Now, what we actually have here is the slope, but then we divide by the price. That way, all bonds can be compared on an equal footing because, of course, not all bonds have the same price. And in fact, some bonds are issued with a higher face value than others. So in order to be able to directly compare them to each other, we have to strip out the effect of the price so that what's left behind is the sensitivity of the bond's price to changes in yields. Okay, so this is our modified duration. And of course, it's the reason, by the way, the reason why that negative sign is there is because people find negative numbers to be confusing. And since we know that the duration is actually negative, at least based on the slope of this curve, by multiplying that definition by -1, it turns it into a positive number because ultimately it's just the magnitude that really matters. So if you're trying to figure out how risky your bond is, the sign is really not what we're after, it's the magnitude. So let's say, for example, I do some calculations. Let's say the duration of this bond is 3.4. Okay, we can interpret that as meaning that if yield increases by, let's say, 1%, or 100 basis points, the price of the bond should fall by approximately, that's the key word right there, approximately 3.4%. And of course, it cuts both ways. So we'll put in here and vice versa. In other words, if the yield goes down by 1%, the price should go up by approximately 3.4%. Now, here's the tricky part, though. The approximation itself depends on the size of the yield change. For small yield changes, this approximation is quite accurate. Okay, now that would mean just like a few basis points, for example. If the yield change is just a few basis points, then the approximation should be very accurate. Like when you start getting into the neighborhood of 100 basis points, which is 1%, then the approximation will start to break down somewhat, because the reality is you are using a linear measure duration to approximate a nonlinear relationship. So in other words, you can imagine that here is our price yield curve. And if we're here to start out with, what could happen, let's call this P star and R star. Let's say down here somewhere, I'll call this R double star. Well, the problem here is that the actual new price is here, P double star, but the approximation, I don't know, call it P double star prime. How about that? Is too low. Okay, it's understating the true price of the bond, and that's because, again, you can see we're using a linear measure to approximate a nonlinear measure. So there's going to be a pretty significant pricing error here. And so the convexity is actually an attempt to capture or maybe improve on that approximation, because it takes into account the curvature of the price yield curve. And we'll see how that works in a few minutes. So in other words, if you just do duration, you're going to get potentially at least an inaccurate look at the change in the price. But if you now combine duration and convexity, you'll end up with something more like this. So here's duration. If you add convexity to that, as we'll see in a few minutes, that will improve the approximation. You're adding an extra term here, which reduces the underestimation of the price. So now all of a sudden, we have a somewhat different result. So it's still not right. I mean, there's still some inaccuracy there, but I think you'll agree that it has improved, at least to a certain degree. And the key here is that what it did was it reduced the underestimation of the true bonds price as a result of the change in yield. Okay, so that's really why this is important, this convexity measure. You can think of it as a second order condition. In fact, we'll see later on that the duration and convexity are actually the first two terms of a Taylor series expansion. Okay, and so we'll get back to that in a bit. But the duration by itself is a linear measure. The convexity adds that extra curvature because it is a second order measure. And so when we bring them together, that presumably will increase the accuracy of our estimates. Now, you're probably wondering, why don't we just use the function itself? Well, it's possible that we don't know the actual functional form of this relationship. All we do have is some observations from the market about different prices and yields, but we may not have an actual formula that we can use here, okay, because we simply don't have enough information to fill it in properly. So that's when this starts to become extremely important. Okay. Well, anyway, so what is the definition of convexity? So since you can see for yourselves the curve is convex, which means the second derivative is positive throughout. And so we don't have to update. In other words, with the duration measure, we know we're getting a negative number, so we make it positive by multiplying by -1, just so that we can focus our attention on the magnitude instead of the sign. With the convexity, we don't have to worry about that because it's guaranteed to be positive. So there it is, second derivative of p with respect to r. Once again, we have to divide out p because otherwise it would be impossible to compare different bonds on an equal footing. Like the ones which have higher face values, for example, would appear to have more sensitivity to interest rates when that's not necessarily true. So these are our two risk measures. Now, we do not have a third order term. If we used one, it doesn't have a formal name because it turns out that the convexity measure itself for many bonds doesn't change the accuracy enough to worry about it because it could be that it only adds fractions of a cent or improves by our approximation by fractions of a cent, and that it's not really worth our while even to use convexity, much less try to bring in a third order term. So this is as far as it goes in practice, first and second order terms, or in other words, the first two terms of a Taylor series expansion. Now, just as this, yeah, and so when you bring them together, if you remember earlier, we approximated the change in the price of a bond with just this part. So here we're adding this extra term, and you can see that because there's a delta r squared term in here, delta r squared is going to be an extremely small number. And so this term might be like such a small fraction of a cent that it may not be necessarily of any help to us. Notice that this is dp or delta p, this is a dollar amount. So this is potentially going to help us, but for many bonds, it will not. So now, as it turns out, the convexity can be very different from one bond to the next. Durations pretty much are related to the maturity of the bond, but the convexity is affected by other factors as well. So let me just show you a couple of graphs to illustrate this. Oops. Okay, hold on a second. I got the wrong color here. So you can see the one on the left has a very low convexity. It's almost a straight line, okay? And then the one on the right has a very high level of convexity. So most likely, the most likely culprit, let's say, for this is that the one on the left is probably a very short maturity bond. Let's say a year or something in that neighborhood. The one on the right is probably a very long maturity bond. But it turns out that the other factors are involved here too, like, for example, the coupon rate will have an effect here. And so what we do know is that some bonds have a relatively low convexity and some have a very high convexity. But unlike durations, modified durations cannot exceed the maturity of the bond because of the way it's defined. So let's say you have a 20-year bond in your portfolio, you know that the modified duration will be less than 20. It might be significantly less, but it's not going to go past 20. That is as high as it can get. The convexity is different. Convexity is a very strange measure in the sense that since you have squared terms in it, Convexity can be in the single digits, but it can also be in the thousands. Okay. So in other words, the convexity measure can be extremely large, but it can also be quite small too. But either way, normally convexity is significantly larger than modified duration. So what that means then is if you go back and look at this formula we are looking at, um, actually it's here it is. Let's get this into the notes. You can see this formula, the second term here, it includes the convexity. It will be helpful if C is a very large number. Okay, if C is a moderately large number or small, because of this delta R being squared, there will be such a small number that unless C is fairly large, this whole term will be quite, let's say, small enough that you could think of it as a rounding error. So normally this second order approximation here is helpful for bonds with very large convexities, which often means very long maturity bonds, like 30-year bonds. Now, other circumstances can affect the convexity of a bond. Now, this is something we haven't really gotten too deeply into just yet, but it turns out that many corporate bonds are what are called callable, which means that the issuer or borrower retains the right to repurchase the bond prior to its maturity date at a predetermined price. All right. So I just want to mention this as an example of how convexity could be affected. And so, for example, suppose that Apple issues a 30-year bond with annual coupons of 5% or $50. Okay. Based on the assumption that the face value is $1,000. So that means if you're buying this bond, you're expecting to get 30 years worth of $50 coupon payments. The investor is expecting to receive 30 years of $50 coupon payments and then have the bond be redeemed at the end of the 30 years. That just means the face value is repaid to the investment. So, in other words, if you drew a timeline for this, here's today, year zero, and you pay $1,000. Next year one, you expect to get a $50 coupon payment, and then another one, and then another one, all the way out. But in the last year, you also get the $1,000 back. So I'm going to write it as two separate terms to indicate that we get $50 every year for the rest of the life of the bond, plus a repayment of the $1,000 at the end of year 30. And this is the set of cash flows that the investor is expecting to receive. But if the bond is callable, let's say in year 25, what that means then, starting in year 25, Apple can repurchase the bond for let's say call price, which is often face value plus one coupon or 10.50. So there's they could come along and say, listen, starting year 25, we're going to just give you your $1,000 back plus another $50 coupon, and that's it. The bond is no longer in existence. So what that means is you're not going to get those last 5 years worth of coupons. So you have to ask yourself why the company would actually do this. Um, Apple might call the bond if interest rates have fallen so that a new bond can be issued with, let's say, a $30 coupon. In other words, they're refinancing it, just like a mortgage. When you have a mortgage, you have the right to, at any time, start all over again with a new lower rate of interest, which is kind of a nice feature. So the same thing's happening here. Apple is saying, listen, if we find ourselves paying these enormous coupons and we can do better in the market with a newer bond, we'd like to be able to do that. So they specify that when you buy this bond, that this could happen starting in year 25. And not only that, if the bond is not called in year 25, it can be called in year 26, 7, 8, or 9. 30, it doesn't matter because the bond is matured. So the reason why I brought this up now is because when the bond is callable, what happens is that there will be some critical yield to maturity below which it makes sense for the issuer to call the bond. Now, there's some threshold we have to reach because there are expenses involved. So it's not going to necessarily be 5%. Here you see the coupons are 5. It's not the case that if rates drop to 4.99 that will just automatically call it back. No, there's other considerations. So but if rates do drop sufficiently, just like with a mortgage, the company's got to have to start seriously thinking about recalling the bond. So what that does to the price yield curve is this. All right, so it's going to end up looking something like this. This is that critical yield I was telling you about. And so what happens is the curve is completely normal from R star up. But once it falls below that R star, the curve starts to bend back on itself. And what happens is in this region of the curve, we have what's called negative convexity. And so that's going to have an impact on the convexity of the bond, and that in turn will affect the sensitivity of the bond's price to changes in yields. So when that happens, and what brought all this up is that in that case, this part of the approximation could have an enormous impact on the price of your bond. Okay, so in other words, if the bond is callable, this part of the approximation could be or have a huge impact on the price of your bond. Okay, now this is doubly important because in the United States, at least, virtually all corporate bonds contain this call feature. Okay, so it matters a great deal. In the treasury market, though, bonds are not issued with a call feature, right? The treasuries, the thing about the treasuries is that, a corporation is borrowing your money to hopefully earn a profit. They're trying to pay for their normal expenses or maybe do some research and development or develop new products or whatever. The government is issuing bonds because they have deficits they have to cover. They've got to make those payments. The government has to pay its bills just like everyone else. If they don't pay the bonds, then they'll lose their perfect credit rating, which means they'll have to pay a lot more interest on all their securities, and they do not want that to happen. So luckily for the government, it has the ability to raise taxes, which corporations do not have. So for all practical purposes, when you buy a bond issued by the US government, you have nothing to worry about as far as getting your cash flows. With a corporation, it's a different matter. Okay. So anyway, so here's our convexity and duration brought together. And if you're only interested in the percentage price change, of course, you can divide both sides by the price and you'll have this instead. The one you're seeing here is the dollar change. Here's the percentage change. Sometimes this is the way to go if you have a lot of different bonds in your portfolio with very different prices. All right. Oops, what did I do? Okay. Now, here we go. Speaking of Taylor series, modified duration and convexity are taken directly from a Taylor series expansion of the bond pricing function P of R. Now, if you remember the way a Taylor series works, is that you've got some function or other, and you have limited knowledge of it. You may not even know the full functional form. You may just only know some parts of the curve. And so what you're trying to do, let's say right about here, we'd like to have a Taylor series approximation. So we can have a linear approximation, which may or may not be very accurate. And then we can also have an approximation which includes a linear term and a quadratic term. And you might end up with something like this. Which is still not perfect, but it's certainly a lot better than just a linear approximation. And if you need the accuracy, you can have as many order terms as you want. You can have a third order term or a fourth or fifth. But with this application in practice, you don't need to go past the second order because anything beyond that would be overkill. It would only affect the approximation by an amount that would be less than a penny. So think of these two as duration only, or the equivalent of duration only, because this is clearly not a price yield curve, but this is the first order approximation. And this is the second. Okay. Now, how does that work? All right, so this is the definition of a Taylor series expansion, which you have seen before in Calc 2. And we have a center, x0 is the center, which is the point that we're trying to approximate the function at. If you remember, Maclaurin series is the one that's centered at 0. The Taylor series can be centered at any point. And you notice the pattern here. We start with f evaluated at x0 over 0 factorial. Then we have f prime, the first derivative, evaluated at that point over 1 factorial. Then we have to multiply that by x minus x0. And then we have the second derivative evaluated at x0 divided by 2 factorial times x minus x0 squared plus dot, dot, dot. We can go out as far as we want. And, there are theorems we can apply to the remainder, but here we'll just stick with this. So keep in mind this F corresponds to the price yield curve. Okay. So I'm going to rewrite it a little bit to reinforce that. So it becomes P of R instead of F of X. That's all. Okay. Remember, R is the yield, P is the price. Okay. So you can see it's the exact same thing. And then you can rearrange it slightly. By the way, of course, these first two terms, we're just dividing by one, so we can rewrite these a little bit. So what I'm going to do is subtract this from both sides. Okay. And this is the change in the price. Okay. In other words, we can replace that with delta P. R minus R0, we can replace that with delta R, just to simplify it a little bit. Okay, so that becomes first delta P equals P prime R0 delta R. All right. Now we can rewrite this as P prime is dP dr. Obviously, it's just a notational change. All right, and so what is this getting us? Well, you might notice since we've defined D as negative dP dr times 1 over P, and C that means that if I divide both sides by P, let's see. Oh, no, I see. Okay, so in other words, this is what we're actually doing. This implies that dP is negative dP over dr, and Cp is d squared P over dr squared. Now we're good, because now you can see that this leaves us with okay. Oh, actually, sorry, this I left out the P's, didn't I? Yes, hold on one second. Let me fix that. Oh, yeah, I'll just move it down here. Yes, in other words, that tells me that we have and then we can divide both sides by P to turn this into a percentage price change as opposed to a dollar price change. And that would give us this. Oh, you know what? Somewhere along the way, I lost the 1/2. Here we go. That's better. Okay, much better. Okay. Wow, that was interesting. So this is the origin of those two measures, duration and convexity, modified duration and convexity. So now, by the way, Macaulay never came up with a measure called convexity. So in other words, remember that the modified duration is essentially an extension of Macaulay's duration, but he never came up with this concept of convexity. So there's only one convexity. We just call it convexity. But with duration, we have to specify whether we mean Macaulay's duration or modified duration. Usually, we're talking about modified duration unless we specify that it's Macaulay. And you can see it really has a lot of convenient properties. Modified, that is. Not that there's anything wrong with Macaulay, but it isn't really meant for this type of thing. Okay, so these are our two basic interest rate risk measures. We don't normally use convexity by itself. We use it as sort of an addition to the duration measure to help improve its approximation. And then often it's not enough to make any real difference. But if we have a case like this, then we really should use the convexity measure. If we have a very simple price yield curve, no optionality, then the duration measure by itself is probably enough to give us a good approximation to what happens to the price when interest rates change. So keep in mind too that the convexity is the sensitivity of the modified duration to changes in yields. Okay, that's what it's there for. All right, so it looks like that's all we have for section 2. So section 3 is where we introduce different alternative types of interest rates. Now, all of these different measures of interest rates actually contain the exact same information, but expressed in a somewhat different way. Not unlike the way we can have temperatures expressed as Celsius, Fahrenheit, and Kelvin. Like, for example, 32 Fahrenheit is the same as 0 Celsius, which is the same as 273 Kelvin. Even though they're different numbers, they actually tell us the same thing. And you'll see something like that happening here. For certain applications, one of these measures is probably the best. So in other words, we have several choices about how we measure interest rates. So we're going to see all of that, right? Well, some of it right now. Okay. So here we go. So now we're ready for section 3. And let's see what that's all about. Here it is, the term structure of interest rate. I think I may have mentioned this once before. If you go to this website, I keep forgetting the exact name of it, but here it is, the daily bar curve. This is what we're after. What you're going to see is all the different treasury securities that are out there, ranging from 1 month to 30 years, and these are the yields to maturity. Okay, so this row, which represents the numerical values of the yields and the maturities, is referred to as the term structure of interest rates. When you see those words, it's understood that you're talking about the treasury market, although it's theoretically possible to do this with other types of interest rates. We normally only focus these on the treasury market. So the term structure of interest rates is a relationship between the yields and the maturities of treasury securities. And these are chosen because they're the safest in the economy, but also because it's the most liquid market in the sense that the volume of trading is so massive that it's easy to buy into these securities or to sell them. And also they're really the only ones that have so many different maturities to choose from. Corporate bonds contain varying degrees of risk. So putting them on a curve could lead to problems. So corporate bonds contain varying degrees of risk and offer very few maturities, meaning typically for corporate bonds, they're typically going to be 10 years, 20 years, and 30 years. Now that's because the company's trying to raise money for long-term investments. Like, imagine Apple saying, we've got to develop another iPhone. We're going to need to spend a lot of money, and we don't have to pay it all back right away. So we'll offer the public bonds that go out 10 years or maybe 20 or maybe 30. These are long-term investments. Whereas the treasury market is different. They're just trying to offer maturities that are convenient for everyone. Because remember, they're trying to borrow your money. They're going to try to make things easy for you. In fact, it's gotten to the point where you can just set up an account online and just buy or sell treasuries anytime you want. And not only that, but you don't even have to buy a full $1,000 at a time anymore, which in the past, that was kind of a big restriction. You're going to buy a treasury bond, let's say, you're going to have to spend at least $1,000. Now they let you buy fractional units for as little as $100 at a time, just to make things easy for you. They figure if it's easy, you're more likely to buy these bonds and keep interest rates as low as possible. So the term structure of interest rates simply means the relationship between all these different maturities and the corresponding yields. Now, if you draw a picture of this yield term structure, the graph of the term structure of interest rates is known as the yield curve, not to be confused with the price yield curve, because this shows not the relationship between prices and yields, it shows the relationship between yields and maturities. Now, in normal times, the yield curve tends to be upward sloping. It's been a while since we had normal times in the interest rate markets here. If you look carefully at these, you'll see that it is up increasing towards the end of the yield curve over here, but you've got this section in the middle where it's sort of dipping down. So these numbers are not normal by historical standards. This is, God, look at what this looks like. It's sort of like dipping down and then dipping up again. That's not normal. Okay. But these are unusual times to say the least. So, the treasury markets, they go through these different streaks of, so you get periods where the yields are very low by historical standards and very high by historical standards and everything in between. So whatever the graph is, it's referred to as the yield curve. Throughout history, it's typically been upward sloping, but not always. Why is that, by the way? Well, the reasoning behind that, well, because of the simple reason that longer maturity bonds have higher durations, which means that their prices are more sensitive to interest rate fluctuations. Therefore, in spite of fact that there's no credit risk in this market, longer term bonds expose investors to more interest rate risk. And therefore, they typically offer higher yields in order to entice investors to buy them. They expect to be compensated for that extra risk in the form of a higher yield. Usually, unless there's something else going on, which is causing all kinds of strange shapes here. But usually this is why the curve is upward sloping. Okay, but everything, things change over time, relationships change. What used to be normal isn't normal anymore. So you can't always go by that, but historically, that's how it's usually been. Okay. And if you go back far enough, you'll see, like they have all these different, like, let's see, what would have been a normal year? Let's try 2019. Yeah, this is a little bit, you can see 240, 242. It is upwards. And there's a dip here too. And you notice the rates were lower than they are now. So, we go through streaks where, let's say if you go to the late 90s, the rates would have been pretty high, a little bit higher than they are now. What's funny about this too, that not all these maturities have always been available. So that's what this NA is for. They go through periods where they sometimes have more maturities, sometimes they remove some of them because they're not selling well. Because these are auctioned off by the Treasury Department, and if people aren't buying, let's say, the 1.5 month Treasury bills, then they stop having them. They stop issuing them. So that's why you see these NAs here. Oh, you can go, oh, this goes really far back. Oh, let's try 2005. Yeah. Well, here it's a little bit steeper. That's one thing I do notice here, that it goes from 1.99 all the way up to 484. So the curve can get steeper and flatter over time too. It's not just is it upward sloping or not, but it can go through streaks where, you know, at the long end, people are more nervous about investing in long-term bonds. That's going to push this relationship up like this, let's say. And so there again, every period in history is a little bit different. So it's possible that at this point in time, people were worried about inflation going up, and they would have required even higher yields to buy the longer term bonds. Because if you have a long term bond, and inflation starts to suddenly rise, you're going to lose a lot of your purchasing power, more so than with shorter term bonds. So that could be one reason why the yield curve is so steep there. But anyway, now, during the COVID, of course, the rates were almost all zeros. I mean, which is not normal at all. Well, they weren't zero, but they're getting down there, and eventually they started to rise again to more normal levels. But these kinds of rates these are very much unprecedented. Except you would have had to go back to the Depression to see rates this low. But it was an unusual time to say the least. So anyway, getting back to the beginning where we were talking about these rates. So there are four basic types of interest rates we may use in our different applications. And you can see they're called yields, which we already are very familiar with. Yields are normally, though, only associated with the bond markets. Okay. When we start modeling derivative securities, you're going to see that yields are not terribly useful. You'll see why when we get there. We're more likely to use what are called spot rates or possibly forward rates. And for some applications, we might use something called discount factors. So all of these, like I was saying before, like think of it as equivalent to Celsius versus Fahrenheit versus Kelvin. They're all related to each other. They're all giving us the same information, but in a somewhat different way. They can all be interpreted a little bit differently. And each of these is a better choice for certain types of products. So bonds are normally priced with yields, but derivatives are normally based on spot rates and forward rates. Because the yields themselves have some quirky features that we'll discuss when we get there. And but luckily we're going to see how to take one set of rates and convert it into one of the other ones in case we need to. So like here's an example of what I mean. Like all those yields that we saw in the treasury market, if we do need spot rates, it's important to be able to take those and convert them into spot rates. So if I'm trying to price, for example, an option on a treasury bond, I'm going to need to have the ability to convert all those yields that I saw in the yield curve into spot rates. So anyway, now the yield to maturity, formally what it means is that you're taking a bond and you're discounting all of its cash flows by a single rate of interest, which is the yield to maturity. So let's say, for example, I have a bond. By the way, this is very, very deep stuff. I mean, you could take an entire semester of just this area, which is known as fixed income markets or fixed income modeling, all interest rates, interest rate based products. It's a very complex but very deep area of study. And people who work on Wall Street, the people who are not that excited by stocks often end up in this area, especially if they have good math skills. It can get crazy mathematical here. The only part, or the only other types of securities that get even more complicated are the derivatives that we'll be looking at later on. But anyway, so having said all that, the price of a bond is the present value of its future cash flows. Okay, so um, and the present actually, let's see if we've got any examples coming up. No, not just yet. All right, hold on. So let's make up a quick example. Suppose a bond has a face value of $1,000 and it is scheduled to pay an annual let's say three more annual coupons of $50. If the bond's yield to maturity is, let's say, 6%, what is the market price of this bond? So what you're basically doing is this. Here's your cash flows. So today's time zero. Now, year three, we get both a $50 coupon and we get our face value back. The bond is redeemed at the full face value. So the value of this bond is the present value of those cash flows, which means, so in other words, you've got the cash flows. In general, you write it like this. So in other words, T is the time index, C is the annual coupon, F is the face value, N is the maturity date of the bond. Okay, so let's get that in there. Actually, it's not maturity date, it's just maturity. How far in the future does it mature? And so the price, P, oh, I should have added that in there. Price of the bond. Price of the bond is the present value of these cash flows. All right, so I am going to pop this into my calculator and let you know what this is equal to real fast. Hmm. 973 point 27. All right. Now, if you were to draw a price yield curve for this bond, it would be 1 point on that price yield curve that we just created. Okay, so now the price yield curve is monotonically decreasing, which means that it has an inverse, which means that if I know the price, I can calculate the yield, or if I know the yield, I can calculate the price. So in principle, I should be able to figure out the yield from the market price. Although we saw in one of the earlier sessions that it's not possible to mathematically invert this price yield curve. Instead, we have to use numerical methods to do that. But the bottom line here is that the price in the marketplace is 973.27. Given the set of cash flows, there is only one unique rate of interest at which the present value of these cash flows equals the market price of the bond. In other words, if I try to discount those cash flows with any other rate but 6%, I'd get a different number. So therefore, yield to maturity can be thought of is the unique rate of interest at which the bond's market price equals the present value of its future cash flows. Right? So that's what the yield to maturity is. Now, it's a very complicated idea, and you'll see that it has some serious disadvantages for pricing other types of securities in the marketplace. So that's why yields are normally only used to price bonds. Their usefulness is limited for pricing other types of securities. Okay. So what else is there? Well, oh, and by the way, here's one of the objections that we have to the yield to maturity. The yield to maturity can be thought of as the approximate rate of return to the owner of the bond. This is only strictly correct if, number one, the bond is held to maturity, which means you don't sell it before the maturity date. And number two, the coupons are reinvested and earn the same rate of return as the yield to maturity. So if these assumptions are not met, the actual rate of return to a bond will differ from the yield to maturity. It may not be very much, but they're not going to be the same numbers. So yields are fine for bonds, but even then they're not completely accurate reflections of the rate of return. So for other cases, we're going to be better off with these so-called spot rates of interest. And if they're not what we need, we can use forward rates and discount factors. By the way, all of the spot rates are taken from the yield curve, and then the forward rates and discount rates are derived from the spot rates. So what we're going to see here is algebraically how to take yields and convert them into spot rates, and then how to do that same thing for spot rates into forward rates and forward rates into discount factors. And then we'll see at the end, we're going to take a bond and we're going to price it in 4 different ways. We're going to price it with yields, spot rates, forward rates, and discount factors. And we're going to see that all 4 cases give us the exact same market price. They have to, otherwise we're changing the rules here. If they don't give us the same price, that means they're not the same rates. Okay, so now this is a fairly complicated process. So I think maybe what we could do is save this part for next time. So, and then I think also we're going to need to do this in Excel because it's going to get very, very messy in a hurry. But when we're done, you're going to have a very deep understanding of how these rates are related to each other and when we can use them for which types of securities in the marketplace. And of course, a lot of this has to do with derivatives pricing, but you'll see more of that when we get there. Okay, so I guess we'll cut it off here and then I'll see you next time.